Yesterday we had a very impactful day, and we hope today we are going to have the same or even more. Like you were told, I'm Dr. Iyambo. I'm a clinical and radiation oncologist in Namibia. Let me first start off by calling our first four speakers to the podium. We are going to have Dr. Vera Ushona. And then our second speaker is going to be Ms. Kaino Haipinge. And I hope she's around. Yes, there she comes. And then we are going to have Leseho Tsie. And then our fourth speaker is going to be Selo, T.S. Selo. Well, we all know that cancer is a time-sensitive disease. It's a devastating news for clinicians to break to the patient. It's a devastating news to the patient's ear. It's also a quite devastating moment for both the clinician and the patient when there is no timely, accurate, and effective diagnostic intervention, treatment, and surveillance for the patients. So, nuclear science application in medicine is of great importance, like we have heard. Yesterday we have heard of the importance and the need for patients to receive treatment in their respective countries. In many countries, especially in the sub-Saharan Africa, cancer patients have become medical tourists seeking treatment in neighboring countries that usually comes at a cost that they cannot even afford. We are fortunate that that's not the case in Namibia. If you find a Namibian somewhere being a medical tourist, it's out of their own choice. So, however, patient deserves to receive the best treatment that there is, irrespective of where they live, and it shouldn't come at difficult financially. So this session, like it was said, is going to unpack the progress and prospect of radiation medicine in Namibia. We hope to be informed as well as be inspired by our knowledgeable speakers and panelists. I'm hoping that the Honorable Governor is still holding the remote to the weather, so we are going to have an impactful and beautiful weather here in Swakopmund. So without further ado, I would like to introduce our first speaker, Dr. Vera Ushona. Dr. Vera Ushona is a medical physicist and radiation protection specialist who holds a PhD in radiation science. She also holds a master's science in medical physics. She specializes in radiation protection and safety of patients, staff, and public. She has more than 15 years in regulatory control of activities involving the use of radiation sources with the National Radiation Protection Authority of Namibia. She is a founder of and the managing director of Metcon Radiation Consultancy. She is the interim president for the Association of Medical Physics in Namibia. She is the vice president for Women in Nuclear Namibia Association. Dr. Ushona also serves as project scientific consultant for the International Atomic Energy Agency project on establishing regulatory infrastructure for control of radiation sources, which is RAF 9070. Ladies and gentlemen, Dr. Vera Ushona, who is going to speak to us on Namibia's overview of nuclear radiation applications in the healthcare. Hence.
Good morning, delegates. Thank you, Dr. Leiner, for that kind introduction. I would also just like to thank the Atomic Energy Board for giving me this privilege to just share an overview of the nuclear radiation application in healthcare in Namibia. I would want to stand on the protocols that were established yesterday, just so that I'm on the right space. Thank you. My presentation today, just going to take us through the journey as to, in healthcare, what are the applications of radiation in Namibia, what do we have, and what are the future prospects. I'm going to look at the use of radiation in healthcare and the main modalities that are within country, and then unlocking as to say, in terms of nuclear technology, what can we benefit, how further can we go in this space. So radiation in healthcare it's one of the biggest use of radiation, basically for man-made sources, and it has been in use for quite a long time. And radiation is used for early detection, for diagnosis, as well as provide treatment in healthcare. So we have three main modalities that are used in the country. We are using radiation in diagnostic radiology, in nuclear medicine, as well as in radiotherapy. When we look at diagnostic radiology refers to the application of radiation where clinicians are able to view what is happening inside the body in terms of the body structures, the bone structures, and we have four main modalities that we have in country. We have a conventional diagnostic radiology machines. We have mammography units, which are used for breast imaging. We have computer tomography. These are mainly used to view soft tissues of organs and tissues in the body. And then fluoroscopy, which usually provide dynamic imaging during treatment or during a procedure in hospital. So in country, currently we have these four basic modalities that we have. Now, when we look at diagnostic radiology itself, the map this is the map of Namibia. So Namibia is divided into 14 regions. Basically, we have the upper north, then we have the central, the west region, the east, and the west. We can see that in the central region, which is Windhoek, the capital city, we have all the imaging modalities are available within the capital city. We have centers that have conventional radiology, we have mammography units, we have computer tomography units, as well as fluoroscopy. Because Windhoek is also where you find the national referral hospitals, so that's why you have all the imaging modalities available in the capital. On my west, on my right, we have the Erongo region where we are in Swakopmund. We can see that all the imaging modalities are also available in the Erongo region to the population of the region. And then in the up north, we have about 4 regions called Oshana region. We have the Kavango East region, and then we also have Oshikoto where we have most of the imaging modalities, but you find that there's still some regions within the country where we have the basic conventional radiology, which is one of the basic tools that is used in terms of diagnosis to provide diagnosis as well as detection. Early detection is available in almost. So you can see in Namibia, all the regions, there is an imaging modality. Radiation is used within or the region. The next application is nuclear medicine. Nuclear medicine refers to where radiation is administered to patients, so either through an injection, then you are able to see the physiological characteristic of the tissue or any organ that was maybe detected as to be an ailment that the clinicians would like to see. So with nuclear medicine, you have radiopharmaceuticals, which are administered to a targeted specific tissue for diagnosis. And then after that process of administration is done, the patient undergoes an imaging either to a gamma camera or a SPECT CT that we have in country. And then treatment of cancer, specifically thyroid cancer, we have an iodine treatment facility for that, and that is for nuclear medicine, where the patient is given the radiation source so that it's targeting the specific organs, in this case the thyroid. Now the distribution of nuclear medicine centers in Namibia. Currently we have 4 nuclear medicine centers, of which 2 are in the capital city, Windhoek. We have 1 here in the Rongo, not so far from where we are, here in Swakopmund, and then we have 1 center up north in Oshakati. So the distribution is 2 are privately owned and 2 are state-owned facility. So you can see in terms of where we are in nuclear medicine, the distribution is only in 3 regions, so there is room to unlock the potential of nuclear science and technology, taking it further to the other regions. With radiotherapy, like the moderator said, cancer is really one of the highest incidents of death in Namibia, and therefore, but being that Namibians do not seek medical, they are not medical tourists, we have treatment for radiotherapy in country for cancer treatment, and we use 2 modalities, mainly external beam radiotherapy and brachytherapy. So brachytherapy refers to the treatment where the radiation source is very close to the cancer, to the tumor, and mainly we use it for cervical cancer as well as for prostate implants, so where the radiation sources are implanted in the prostate for the cancer treatment. For external beam, we have 2 modalities, one that uses a radiation source called the Cobalt-60 machine, and then we have a linear accelerators that uses high energy photon beams for cancer treatment. Now the distribution of radiotherapy centers in country, currently we have 2 radiotherapy centers. We have Dr. A.B. May Cancer Care Center, which was established in 1997 and still going strong. It has provided cancer treatment to millions of people in country, and as you can see, it's located centrally in the Commerce region. Everybody from the country has to travel to the Commerce region to seek for the treatment of radiotherapy. 1 center is a private center called Namibia Oncology Center. If you drive here going to Cottage Hospital, you find this Namibia Oncology Center, but here in the Rongo region, they do not provide radiation therapy. They only provide chemotherapy, so radiotherapy in country is provided only in Windhoek. So what are the future perspectives when we look at the use of radiation in healthcare in Namibia? There is room for expansion of our nuclear medicine facilities, as well as looking at the radiotherapy services to the other regions outside the capital city. Investment in advanced imaging technologies. As much as we have all the basic imaging modalities, we are able to do detection, we are able to do treatment, and also provide diagnosis. There are other advanced imaging modalities that are available, yet we still do not have them in country, such as we have positron emission tomography, computer tomography, imaging modalities, as well as one key aspect when you look at nuclear medicine is production of radiopharmaceuticals. Currently, all the radiopharmaceuticals are imported. In country of the majority comes from South Africa, and especially during the COVID, you see there was quite a delay in getting these radiopharmaceuticals to the patients. So investment in the production of such a facility, a cyclotron, that will be able to enhance and unlocking the potential of radiation in healthcare. So in conclusion, radiation does play a critical role. In Namibia, we are able to provide the basic imaging Also advanced, we have the advanced technologies, especially even in radiotherapy and in nuclear medicine, but opportunities do exist that we can expand more in this, looking at the advancement in the imaging technologies, as well as also in the treatment. There is treatment, people are using proton therapy for cancer treatment, so the sky is the limit in terms of using radiation in healthcare. With that, I would like to thank you very much.
Well, once more, a hand for Dr. Vera. Obviously, as an oncologist, I can't say enough for when it comes to the importance of diagnostics for me to give proper treatment to my patients. I need my patients properly staged. I think to that list I'll add an MRI, a quite important component that can do so much, especially in the absence of a PET scan. And also not to forget our laboratory services, although it doesn't form part of nuclear sciences, it's one of the important components in cancer management. So once again, I hope questions will come up and we will be able to answer. So we want to manage our time well, just in case it's one of the criteria of the honorable managers to, in his own words, be nice to him. So let me introduce our next speaker, who is Ms. Kaino Haipinge. Ms. Kaino Haipinge is a clinical medical physicist working for the Ministry of Health and Social Services at Radiation Oncology Department, and she also supports diagnostic imaging department in the country. She's the country chief scientific coordinator for the IAEA coordinated research project on standardizing medical physics for diagnostic radiology. She holds a master's degree in medical physics and currently pursuing her PhD at the Namibia University of Science and Technology here in Windhoek. And I'm also happy to announce that I am her boss. Ms. Haipinge is going to talk to us on the role of key professionals in advancing radiation medicine. Ladies and gentlemen, hands up for Mrs. Kaino.
Good morning, ladies and gentlemen. Thank you, Dr. Yambo. First of all, I would love to give my appreciation, my utmost appreciation to the Ministry of Health, Atomic Board of Namibia, as well as Namibia University of Science and Technology. So I'm here to deliver to you the key role profession in advanced radiation medicine. So adding on to what Dr. Vera had said. Which side do I go? It's not moving. It's stuck. Why my slide look like this? Not sure. I'm not sure if IT could verify my... Yeah. Okay, on the background, basically just the radiation medicine that's rapidly evolving in the country, Namibia, a profession that relies on experts of various professions to provide safe and effective treatment to the patients. These professions are supposed to be a multidisciplinary team that work together to provide patients with the best possible care. No, something happened. I'm not happy. This is not what I have on my, yeah. Yes, we can do this. Thank you. So their expertise and collaborations are essential for advanced field of radiation medicine and improving the patient care. Who are they? So this multidisciplinary team would be comprised of a medical physicist, a radiologist, radiographers, radiation oncologists, medical dosimetry, radiation therapists, nuclear medicine physicians, nuclear medicine technologists, and radiopharmaceuticals. So why medical physicists at the top of the list? The medical physicists would play a major role in the safe and effective I'm so sorry, I'm just not happy with my slides. I didn't submit them like that. So the medical physicists ensure the safe and effective use of radiation delivery, where we are mostly involved in designing of an equipment that we want to deliver a certain kind of radiation to the patient. We are then involved in procuring the equipment and making sure we give the specific that we desire according to our demands. You know your country, you know your patients and all that, so you come up like, this is the kind of equipment we are looking for, these are the specifications we are looking at, so this is what we are able to work with. Depends on the experts that you have at hand. When your machine comes, then as a medical physicist, then you have a responsibility to calibrate and commission that machine before it's put to use. So in essence, that it gives the output of radiation that desired for certain and specific type of tumors, working in hand with your radiation oncologist. Let me see. Yes, correct. We are also responsible for developing treatment plans. This is to maximize the tumor dose while we maximize the organs at risk on the specific patient, on the specific cancers. While doing so, we monitor the radiation safety procedures as the patient is going through the treatment. On the next, the radiologists, they follow the medical physicists because for the patients, they need to be diagnosed. The radiologist has to work hand in hand with the laboratories, pathologists to rule out what what has changed in the cells. So then they have to come and do the diagnostic. They have to come and do the diagnostic interpretation of images, examine the images created by the radiographers, and identify the abnormalities, change that were detected at the laboratories, and consult with the other health cares, which might be the radiation oncologists and nuclear physicians, in order for them to do a constructive diagnosis and to plan forward for what's necessary for the patient. The radiographers, then they help the radiologists to perform diagnostic imaging procedures for them to come and read those images. They operate on the different equipment that were earlier explained by Dr. Vera. They play a role in positioning the patient correctly for imaging. They ensure the safety of the patient during those procedures, and they prepare images for interpretation by the radiologist. The radiation oncologists, like Dr. Yambo herself, they are responsible for evaluating patient for suitability and radiation therapy. When now the radiologists, the labs have confirmed a certain cancer on the patient, then the radiation oncologists have to come and decide what treatment that's suitable for this patient. They are now going to then develop a treatment plan in collaboration with a medical physicist. Alongside the treatment journey, they will be monitoring the patient progress, and after the treatment has been completed, alongside they will be consoling the patient alongside with their families as they battle the cancer treatment and how to navigate through that. And also, they have a responsibility to keep updated on the latest advancement on the radiation oncology field. We have specialists which are called medical dosimetrists. At the moment, we don't have any in Namibia. And their roles are to work alongside the medical physicist and the radiation oncologist to make sure that when the treatment planning was planned and designed for that specific patient, they are now go in to calculate the radiation doses that to be delivered to a specific patient for a specific cancer, using a specialized software to create treatment plans. These are called treatment software plans, TPS. And also they have the duty to verify the accuracy of the dose calculation. This has to be done alongside the medical physicist so that you make sure you delineate all the organs at risk and you are ensuring the compliance with the radiation safety regulation. For Namibia, in this case, it's the National NLPA under Atomic Energy Board. We have the radiation therapist. After the process of screening the patient is being done, the treatment plan has been designed. Now the patient has to go to the machine because now the dosimetrist and the physician has sent the plan that was algorithmic to the machine. So now the patient have to go and be handled by radiation therapists, also other key role professionals in the field. They will deliver the radiation as prescribed and supervised by the radiation oncologist and the medical physicist. Operating the radiation therapy machines, they will be positioning patient accurately for treatment, and here we should also know that they will be using some devices for immobilizing the patient so the patient wouldn't have to move and then in the process you miss where you are supposed to be treating. At the same time, they will be monitoring radiation dose delivery as prescribed and ensure the patient comfort and safety. This is where all our immobilization devices are also very, very crucial, and it's the radiation therapist's duty to make sure that the patient is safe. We go back to nuclear medicine physicians. They belong a little bit to the diagnostics because here they will do diagnosis. And but the difference is they are using radioisotopes. We have one department at Central Hospital and two others that, like they were mentioned by Dr. Vera. So they will be administering radioactive tracers to the patients and interpreting images produced by the scans, by the diagnostic imagings. Currently in Namibia, we only have a SPECT, we don't have PET yet. I hope it's something that's in the pipeline. It will make a great difference if we could get one. So mostly what is being treated right now is the thyroid disorders. Then they are using the radioactive isotopes to make sure that that's delineated from the patient's cells. They work alongside the nuclear medicine technologies that will make sure that they are assisting the physicians in performing diagnostic procedures to deliver those radioactive isotopes. They are the ones that are preparing them. They are the ones that they do radiation protection for patients that are going through radioactive isotopes procedures. They are the ones that are doing QA and QC on the specs that we currently have on the equipment that will be used to trace and take the imaging for that. They are also responsible to assisting with patient care. We have the most important people, which are radiopharmacists. The radiopharmacists are people, it's a profession of pharmacy, but now it's a pharmaceutical that use radioisotopes to prepare and radioactive medications for patients who are going through cancer treatment. There is a designated pharmacy at every radiation oncology department. Either they are going through chemotherapy, either they are going on radiation or on nuclear medicine. So someone has to be sure to make sure the accuracy of the dose that's being prescribed and the sterility of that, it falls in the same order, so there should be no any other hazard that will come along that. So the most important thing is the quality control, how they conduct quality control tests on radiopharmaceuticals to verify their potency, the purity, and suitability for use. So before these are delivered to the patient, the radiopharmacists have the responsibility to make sure it's something that's safe, and then they will advise the clinicians, both the oncologist and nuclear physician. Then they will then be able to dispense them and administer them. You will prescribed for chemo. These are the people that have to come and dispense that, mix it, and give it to the nurses, or they come and administer them themselves. They also have another responsibility for various medical procedures. For instance, you are going for an imaging and you need to have a radio isotopes beforehand. They are the people responsible to make sure you get this amount, it's going to last for how long, and the procedure will be lasting for how long. That's their job as a radiation safety, to make sure it's nothing that harms you, harms the healthcare that are dealing with you, and also it doesn't harm the public when you go out to your family. They also do patient counseling. I think this is everyone's duty who is in a radiation medicine. We all go through that. And there's a lot of research and development that need to be done. And it's the only way we can go ahead. And so we also need to have a radiation safety officer. I myself am an accredited radiation officer by the Namibia Uranium Institute, maybe 4 or 5 years ago. So our job is to ensure that the Department of any department that deals with radiation oncology or all that, to ensure compliance with the regulations. We need to have a licensed department, a licensed machines, and our healthcare workers need to be protected. They have to be wearing their TLD badge, and they have to be returned on time. We have to receive and monitor the dose of those that work in the radiation. The patients at the waiting areas, they are safe. It's always under the minimal prescribed dose. And we are also developing and implementing radiation safety procedures for the department. Like in Central Hospital, we do for diagnostic department. Like it said that I'm supporting the diagnostics, monitoring radiation exposure levels, conducting radiation safety trainings to train those that are coming to the department. This is a department, a special department. This is how you behave in this department. This is how you handle ABC and all that. So also we do the investigating radiation extent and incidents. Just, you never know, anything can happen anytime. We have to be on our guard to make sure nothing happens and how it's being handled. Before I go to the conclusion, I want to give an overview of different personnel that we have as per the regulatory body, because in Namibia we have to be registered with Health Professional Council of Namibia, and the statistics that we have as of 2024, in the state we have 5 medical physicists. They are all working in Windhoek, and they are all working in radiation oncology. We have 3 radiologists. We have radiation oncologists, and there are 2. Dr. Yambo makes one of them. We have radiation therapists, and these are the most important people because the workload of patient falls on their shoulders, and there are only 5. Catering the whole country, as Dr. Vera has indicated on her map, that the only center for the state is in Windhoek, and the whole country would flock to that central part for treatment to be treated by 5 people. We also have a nuclear medicine physician. There are 2 in the country. They are working for both state and private. And the people that are supposed to be dispensing the radioisotope medications, we have 0 in the country. Yes. This is my presentation. Thank you very much. So maybe I can just add a little bit to the conclusion that there is so much need. There is so much need for training for these personnel. So we have to come together and do a lot of sponsoring, or people should be willing to go and study. So in essence, above all, the profession, including laboratories, diagnostics, and everything, everyone plays a major role in making sure the radiation medicine is a field that it is. Thank you very much.
Well, thank you, Dr. Kaina, in the making. I'm sure you won't find such uniqueness anywhere else in the world, where you have more medical physicists than oncologists in a department. Welcome to Namibia. Well, you have heard it, that cancer management is a multidisciplinary team. It's supposed to be handled multidisciplinarily. We need to understand that the presence of any of the professions does not make up for absence of one. So we need all those professionals as they are. And as I have heard, there was a pre-conference session with some students. I hope we have done enough justice. We have given out information. We need to be going out to career fairs or wherever it is where we raise awareness, because as much as we are saying the first cancer center was established in 1997, it seems we still don't have enough awareness in the country as to which professions are needed to work in the cancer center. And specifically when it comes to nuclear medicine, we all know that prostate cancer is one of the most prevalent diseases in Namibia. And I mean, how it's different from other is that its staging is mainly through nuclear medicine. We need SPECT-CT. I mean, the world has moved to PSMA, PET, and things like that. But in the absence of the advanced, we still need to have basics. So these are things we need to seriously look into as a country, especially in the room where you have all the different stakeholders that can help us move forward as a country. Who said women are not good time managers? We are still on time. So, without wasting much time, it's my pleasure now to introduce our next speaker, Lesego Tsie. Is a dedicated shift production manager in molybdenum 99 production facility. As the first lady to work in the production of the radioisotopes, she is passionate and goal-driven individual who believes in women empowerment in a male-dominated environment. During her 15 years experience, she has overseen the production of high-demand products, ensuring timely delivery of decay radioisotopes and adhering to quality and safety standards. She worked with companies in a variety of industries like mining, education, and currently pharmaceutical. Ladies and gentlemen, Ms. Lesego Tsie is going to speak to us about application of radiation in medicine, that's diagnostic, nuclear medicine, and radiotherapy. Hands for her, please.
Good morning. Good morning to all the delegates around us. My name is Lesego Tsie. I come from South Africa. I worked at NTP Radioisotope SOC Limited Company, a subsidiary of NEXA, which is South African Nuclear Energy Corporation. NTP is a company that produces and supply radio-based products around Africa and around the continent to more than 50 countries around the world. Like she mentioned, that I oversee the production of molybdenum 99, ensuring the timely delivery of the isotopes. NTP produces active pharmaceutical ingredients. Oh, sorry. My next slide. Is it fine? Okay. Okay. With my introduction, NTP produces active pharmaceutical ingredient products, which are the fission molybdenum 99, iodine 131, and lutetium 177. NTP also distributes pharmaceuticals, namely the F18 FDG, technetium 99 generators, and the labeling kits. Let me give you a quick description regarding our process, our active pharmaceutical ingredients, which is the molybdenum. Molybdenum 99 is produced from irradiated target plates, and it's sourced and prepared in a reactor. Reactor is the one that on my slide is at the top, and is prepared and sourced from the Safari reactor, transferred to radiochemical facility. The targets are then handled in a hot cell complex, which is the gentleman with the manipulators over there, to process the molybdenum 99 chemical processes steps, and is dispatched and sent to customers according to customer specification. Further process of the molybdenum 99 are the technetium generators, which are the one that's written Novatech at the bottom, which are distributed to hospitals and clinics for medical imagery of visualized functions of organs and tissues in a human body. And another API that we have is iodine 131, which is produced as a byproduct from the molybdenum production. And the iodine is used for thyroid diagnosis and therapy. Iodine, those are the capsules underneath the lady there on my right-hand corner of the slide. And then lastly, the lutetium-177 is produced from radiochemical separation. That is the gentleman, the little lady, and the lady on the right-hand side. And it's done from a radiochemical separation from bulk irradiated ytterbium-176 targets. And lutetium is used for treatment in cancer and therapy, and prostate cancer. Looking at the radiopharmaceuticals, like I've mentioned earlier, technetium-99 generators are prepared and they labeled and partnered with radiopharmaceutical agent in order to reach the targeted areas in the human body. The regenerators are labeled with kits, or called kits if you have to call it, for the use for imaginary different body parts in the body. And then at NTP, we supply different pharmaceuticals around the world, like I mentioned. We have the MDP, which is used for skeletal system, the Renatec, which is used for the kidney, and Decida, the liver and the gallbladder, the tin colloid, which is for liver functions, and we also have the RBC, which is for the red blood cells. One of the pharmaceuticals that we have, which is the F18FDG, is used in application of imaging and staging of neuroendocrine, and then the PSMA is for prostate imaging. Now that we have looked into what NTP supplies, we can come to the definition of what nuclear medicine is. Nuclear medicine is highly effective, contributing to treatment of patients using radioisotopes. The medicine is a radiopharmaceutical to visualize and access the physiological functions and accurate diagnosis of various conditions, namely the cardiovascular and diseases and neurological diseases. Nuclear medicine basically helps to identify the tumor and early detection of cancer cells spreading to other areas in the human body. Now, when it comes to our distribution in Africa of nuclear medicine, I can say we've done quite well in Africa, but the most African countries participating in the nuclear application, it's South Africa, Egypt, Ghana, Morocco, Kenya, and Nigeria. A bit of a background, in the 80s, Algeria, Egypt, and South Africa started the SPEC nuclear medicine imaging, and in the 90s, Morocco, Tunisia, and Namibia followed, and in the early 2000s, it was Libya. So nuclear medicine has increased exceptionally in the North Africa and South Africa. For instance, in Egypt, the PET scans for cancer diagnosis and treatment were established. Now we have the growing nuclear medicine services in Kenya, innovation to support remote diagnosis in Nairobi, development of nuclear medicine centers in major hospitals in South Africa leading in molecular imaging. We have that at the moment. So coming to the footprint that NTP has in terms of distribution and supplying of the nuclear medicine around the world, those are the countries we are currently focusing, supplying and distributing our nuclear medicine. And on my left-hand side, those are the African countries that we supply our nuclear medicine at. Obviously, we need a lot of improvement in terms of nuclear medicine is concerned, but those will tap in when I go through the challenges that we might face in terms of supplying that. The next slide, distribution of nuclear medicine in Africa. This is our African continent, and then the machines that are available, those are the countries that we have no machines. These are the blue ones, and one machine is the ones that labeled with the green, and the brown is between 2 to 3 machines, which means we can grow and do more innovation in terms of getting our radiation medicine to be number one. Coming back to the challenges, key challenges that we have in terms of distributing nuclear medicine. The key challenges, which are the limitation and the stumbling block in terms of producing and distributing nuclear medicine. Firstly, since we are working with radioisotopes, we have the half-life, the short half-lives that we have of nuclear medicine because of the decaying nature of the radioisotope. So in terms of distributing to other areas, it's impossible and sometimes a little bit hard. Like for instance, molybdenum-99 has a half-life of 2.75 days. Iodine-131 has a half-life of 8.04 days. And lutetium-177, non-carrier added product, has a half-life of 6.647 days. And then secondly, obviously, our challenges is funding and resources. The high cost of diagnostic procedures that limit the access, especially in the low-income African countries. And lastly, the shortage of trained profession in this field of work make it a problem in terms of distribution of nuclear medicine. So how do we come to exercising and dealing with those challenges? Which comes to my conclusion. Obviously, we need collaborations, partnerships. We need government collaboration with healthcare providers and industry stakeholders to expand and attract young generation, and the government deployment of legislation to curb the need and the supply to populations that are economically disadvantaged in Africa. And more facilities of educational institution is needed to enhance and emphasize the nuclear medicine around African continent. Critical trainings in schools, colleges and universities are crucial to establish educational programs to make sure that nuclear is appealing and fashionable to young generation. And obviously the last one, which is the one that is needed, I think, in all the African countries, it's enhancement of public and private hospitals, facilities, partnership, so that the medicine reach the people who need it around the world. Thank you for your time. That is my presentation.
Whoa. If any of you in the room is like me, who only knew the first two rows in the periodic table, I think it's high time you go back and just make sure you study all the other remaining chemical elements, because wow. Now, the one thing with advancement in medicine and specifically in oncology, it's like things move at a sort of catch me if you can type of thing. So if you're static, you remain there. But I have great hope for Namibia. One day we will get there, one brick at a time. So now our last speaker before the tea break has got quite an extensive bio. I'm going to try and go through. Mr. Tato Selo, who has interest in science since high school years at King Edward VII School. He matriculated in 2001 and studied further to a master's degree in chemistry at the University of Wits. He joined NEXA in 2008 as a research scientist, focusing mainly on radioorganic chemistry, fluorine 18. In 2013, he was awarded the IAEA fellowship to the Cross Cancer Institute, University of Alberta, to learn more about the topic on fluorine 18. This also involved the use of remote synthesizers, units for production of radio traces for different applications. Also built and ran an in-house remote synthesis unit for the production of fluorine 18 radio tracer for brain function studies. He then moved to work for Sasol Chemicals under the Nitro Division as a senior scientist, supporting both the fertilizer and explosive business. He again joined NEXA in 2019 as a senior scientist involved in research and development of radiopharmaceuticals under GMP protocol. This includes production of radiopharmaceuticals for clinical trials. Currently working on the TB161 project that involved the feasibility study to produce and supply TB161 radiopharmaceuticals for the treatment of cancer. Mr. Tato Sello is going to be speaking to us about the production and use of the beta and omega emitters, TB161, and the future of radioisotope for cancer treatment. Welcome to the podium, Mr. Sello.
Good morning, everyone. I wasn't quite sure about the Bible, but it's the first time I hear someone actually reading my biography. It's quite amazing sometimes. Anyway, my name is Tato Sello, as mentioned. This morning, I will be talking about Tebium-161 as a future radioisotope for cancer therapy. I work for the GMP formulation group under applied chemistry, and within this space of work, my colleagues I'd like to acknowledge at this moment: Judith Wagner, Janine Suthiram, Lebusipini, and Jan-Rein Ziefert, and V.D. Mullen is a professor in Switzerland. So this work is in collaboration with them. So my presentation outline quickly, it would be looking at the different technologies around the world that are used to produce the Tebium-161, the challenges that are faced with each of that technology, and then we're going to a little bit compare the golden standard lutetium-177 to the new kid on the block, which is Tebium-161. We'll also look into just a little bit on the good manufacturing practices, and then finally, a proposed potential synthesis route in terms of producing the Tebium-161, and what would you need in essence of participating in the Tebium-161 market. All right, so what is Tebium-161? So it's an element, it's a lanthanide, but you've got then a quartet of isotopes that occur within the Tebium space. So you've got Tebium-152, which is a positron emitter, and that can be used for positron emission tomography, PET. And then you've got Tebium-155 that emits gammas. You can use that for SPECT imaging. And then you've got Tebium-149, which is the only alpha emitter within this group, and you can use that for alpha therapy. It does emit a little bit of positrons, so not much in relation to Tebium-152. So yeah, you may try use it for PET as well, but it wouldn't be necessary since you've got the Tebium-152 in this case. And then we've got Tebium-161, which we'll be looking at, which emits both the betas and the gammas. And this is then used for beta therapy. So the next slide is basically the same, but it tries to explain how we actually produce the four. So on the left, you've got the radionuclide production, which you can produce in an array of ways, so by bombarding with neutrons, protons, gammas as well. And then we take that, we complex it with an organic molecule, and then from there we do preclinical studies. So the slide tries to explain basically the process that occurs within the value chain of the Tebium itself. Right, so in essence, terbium is more similar to lutetium-177 by nature. So it would have the same beta energy decay. The only the same half-life as well, 6.7 days versus 6.9 days. And then it decays to stable daughter isotopes, hafnium-177, and then dysporium-161 for the terbium. However, the difference between the two is that the terbium emits over and above the beta radiation. It emits conversion and OJ electrons. And then also the nuclear availability, research is still going in that space of trying to produce the terbium-161 as compared to the lutetium-177, which is readily available and is currently in the market. All right, so initially I said the terbium-161 is a little bit similar to lutetium-177. So what do I mean by that? I mean they both occur in a trivalent state, so +3 state, and the ionic radius of both the lutetium and the terbium are similar. So this means that chemistry-wise, the terbium and the lutetium would behave similarly. So therefore, one of the advantages of actually putting terbium into the market would be that the same the chemistry production protocols that are done using lutetium would more or less be the same as the terbium. So it's more like a plug and play type thing. Now you would be asking yourself, why do we, if we have lutetium which is already in the market and it's doing very well, why would you then want to introduce the new kid on the block, which is the terbium? Simple reason, over and above the beta radiation that terbium is producing, it produces also, like I said, the conversion and the OJ electrons that focus mainly in zapping the monolayer cancerous cells. So the cells that may not even appear on your PET scans and that are responsible for relapse. So that's basically the reason why one would actually get to be interested in the terbium versus the lutetium. So on the slide at the bottom, you've got a lutetium-177 complex structure. So in green, it's the macrocyclic ring that actually encapsulates the metal itself, the isotope itself, because the isotope on its own would be poisonous or toxic. And then the black structure with blue is basically a should you call it a key? So in other words, your cells has receptors, which you would imagine as locks, and then that black structure comes and docks onto the cell, which is the key, and unlocks it so that the radiation then is accepted by the cell and then is working from the inside of the cell rather than the outside. So basically that's the mechanism of actually killing most of the cancer cells. Right, so how do we produce terbium-161? So groups around the world have been working on this, so I'll be just touching base on a number of them and sharing that information in that regard. So Lebenberger is a scientist who in 2011 suggested that we could actually replace lutetium with terbium-161. The only thing with his work is that he was focused more on having to produce it from the gadolinium-160, but gadolinium nitrate is that he started with. The only problem is that the starting material is hygroscopic, meaning that it's water-loving. So you tend to introduce a little bit of moisture within the starting material. That also makes the starting material a little bit unstable, and also a little bit of risk, not a little bit, but risk in terms of having to bombard that in the nuclear reactor, simply because that you then form water vapor that may cause pressure within the ampule, and you can imagine bursting of the ampule and everything falling on the floor. And then also the yields of the product itself are very low because of these reasons. Another group in Russia, Moscow State University, tried to produce Terbium-161 from Diasporium using a photonuclear method, and also the final product yield was low, but over and above that they formed Terbium-160, which is another isotope of terbium, which is long-lived, and it's an impurity within the product itself. And also, the challenge with this is you can't separate Terbium-161 from Terbium-160 since they're similar in chemistry, so there's nothing much you can do in that regard. Another group in Brussels used a cyclotron to try and produce Terbium-161, and then they also ran into the similar problem of having to, on the same length as producing Terbium-161, produce the long-lived isotope Terbium-160. That is an impurity that you don't want, and therefore they ran into those problems. And as I said before, you can't separate the Terbium-160 from the Terbium-161, and you don't want to be introducing a long-lived isotope in a patient, so that would have to then come to a stop. Right, so then you've got the neutron irradiation production of Terbium-161, which I was talking about. Though here the only difference is that the institute in Switzerland, which is the Paul Scherrer Institute, managed to come with a way of actually making the production of the gadolinium nitrate a little bit better. So instead of starting with the nitrate, like I said, which is hygroscopic, they started with the gadolinium oxide, which is a little bit more stable. So what they did was they then managed to develop a way of processing this gadolinium oxide, and they sent it to different reactors for study. So they sent it to the ILL nuclear reactor in France. They sent it to us Nexa in South Africa, and they actually also did a little bit of study in Switzerland, the SynQ reactor. So however, you may see that in the SynQ reactor, they actually tried to irradiate the nitrate. What I didn't add here is that they then did a study of comparing the nitrate and the oxide of the gadolinium, and they actually found out that the oxide has a higher yield as compared to the nitrate, which talks to the same results as what they had gotten before. So those are the results on the right, and it came out pretty convincing that the oxide is much more the starting material to follow in relation to producing the Terbium-161. So, summary, your time-consuming target preparation for the nitrate, while for the oxide it's a simple target preparation. In terms of the chemistry, like I said, because the nitrate is water-loving, so therefore you may deduce that chemical separation would be easy because it dissolves much simpler as compared to the oxide, which doesn't. The nitrates are hygroscopic, and then they may affect the result because of that water-loving nature. And then the oxide is a little bit more stable in relation to the nitrate. Right, so now that we've covered a little bit of the worldview of how they produce Terbium-161, I need to then focus on what works. So in this case, it was a study that was carried out by the Paul Scherrer Institute in collaboration with Nexa. And basically that's pictures at the top show you the ampule on the left with gadolinium oxide, and then the irradiation, and then the chemical process. And what they do after the irradiation, going into the chemical process, is that they use what we call a SiChem resin, and then the alpha Hiba as a mobile phase. So basically try to separate the good stuff from the impurities. And then from there, you basically take the separated liquid phase and you try to reduce the solvent. So you reconstitute it by using another column called the LN3, which is just a fancy name for that column. So then in that case, we elute it with hydrochloric acid, which then will be good enough for one to take further for labeling studies or using it for other things. This is just a schematic diagram showing the semi-remote synthesis system that is used to purify the terbium-161 from the crude material that you get from the reactor. And in this case, you get a separation yield of about 80 to 90%, and an activity concentration of 11 to 21 megabecquerel per microliter. Okay, so these are the specifications of the commercially available lutetium chloride versus the terbium chloride. And as you can see, they more follow the same specification, though the difference is that you get a little bit more in terms of gamma ray spectrometry and then the radio TLC. And it was also found, interestingly enough, since the terbium is a beta emitter over and above emitting the OGN conversion electrons versus the lutetium-177, which is only a beta emitter, what the show here is even though the terbium emits these extra radiations, the stability is still more or less comparable to the lutetium. So terbium-161 complexes versus lutetium-171 complexes, they behave the same in terms of stability. Right, so another group tried to purify the terbium-161 using a commercially available remote synthesis unit. So this unit is a Eckert and Ziegler. It's quite a nice unit. We also have it at Nexa. And so basically now he was trying to simplify the whole entire purification process using a machine that is GMP compliant. So this is where we're going now. So we started with the science, and then we went into a space where we could try and come up with specifications for the terbium chloride. Now we're moving into a space where we try to make it GMP so that we can start using it in patients and clinical trials. So he was one of the guys who tried to get it into that space, which then leads me to my next topic on my presentation is what exactly is GMP? So I've spoken about GMP a couple of times, but what exactly is it? So GMP is a quality management system that basically forces you to produce a radiopharmaceutical or any medical product within specifications that are acceptable for one to use it in a setup of a hospital or clinical trials or something to that effect. So it has a number of layers within its framework, but mainly to address the issue of having to produce this product in a sterile manner. So in other words, you don't want to be producing anything that has a capability of actually making the patient sick, in terms of something else being introduced in the product that is not supposed to be there. So in essence, this is what it looks at. It looks at the people. If you look at that the circle diagram of there, so it looks at the people, for example. What does it mean? It means that the people must be trained, certified, and be able to to show that what they are doing is actually what they are supposed to be doing in the correct manner. It looks at premises. So in other words, are your premises good enough for one to produce a product that is sterile in nature? And are the premises geared in such a way that they allow you to actually do that? So for example, you would work in a clean room which has a different flow of air, so the air has to be filtered, temperature, humidity has to be monitored. So you must have a system that actually monitors all those factors in relation to the product that you're going to be producing in that facility. Processes and procedures look at your instructions. In other words, your SOPs must be in order. They must document. They must be traceable. All the material that are coming into the clean room must be documented. They must have a certain system that receives them from the manufacturer. They must run with a CO. They must come with a COA that, if you run the same tests, must give you the same results within the space of that COA, and they must actually then work in producing the product that you're supposed to have at the end. So in other words, all these processes must be traceable to a point where, should anything go wrong, you need to pinpoint exactly where the problem may come from in relation to the whole quality management system. Right, so this is another diagram that shows you where our group normally functions. I should add, this is so like a generic diagram that actually explains exactly from idea phase to market phase how maybe the process would go. So you've got on the left basic research, and then preclinical animal studies, and then from there, once your product is so like semi-developed, we try then to take that and produce it under sterile conditions. That's where our group functions, CGMP, and we take whatever that a scientist or whoever has a product that has potential, and we try to produce it in such a way that then it is accepted for clinical trials. Or the CGMP can be moved over the green section to where now we are doing market studies. So in other words, there's a product that already exists. It's been proven. It's got all the methods that comply with the CGMP or GMP quality management system, and we receive that and we try to produce the product under those conditions to see how the market would consume or accept the product, or to try and see how exactly we penetrate the product moving forward into the market. So in terms of the Terbium 161 development, you would have also following the same process. So the production on the left, and you would have scientists and researchers trying to play around with it and see what it can do, and then it would then move, into the characterization stage. So that would basically be the stage where now GMP is introduced. So you would then develop your specifications, you would then develop your processes, your instructions to try and make it GMP compliant, and also your quality control checks that are needed to qualify the product. And then on the right hand side, after you've qualified and made sure that your Terbium 161 product is GMP compliant, you would then use that product to label it and produce radiopharmaceuticals, like, as mentioned, the PSMA as one of the products for the treatment of prostate cancer. And that also would need its own processes, quality control, and so on and so forth. But in essence, so the terbium 161 itself is where NECSA is actually interested in. That's where our focus is, to try and make sure, or to try and get into a space where we actually develop and produce terbium, GMP compliant terbium 161. All right, so there's a catch. Two companies that saw the potential of terbium 161 went out and bought all the starting material globally. One company has 1/3 of the starting material, and the other company has 2/3 of the starting material, simply because they saw the potential of terbium 161. So for other organizations to try and get into the market, depending how quickly you want to get into the market, it would probably be advisable to actually try and collaborate with these companies, simply because currently there are no companies that are producing the starting material. I think Russia and America are interested in starting the program, but it's not yet something that is finalized. It's stand to be corrected, but as the last time as I checked, these are the only two companies that have all the starting material that exists in the world, which is the gadolinium oxide. So in conclusion, terbium 161 is a new kid on the block. Lutetium 177, which is accepted by the market, was